Nothing about a black hole should be visible. Light can't escape one. No camera has ever photographed one directly, and no spacecraft has ever sent data back from one. Yet a team of radio astronomers built a telescope the size of Earth itself just to look anyway. What they found changed physics forever. In November 1915, Albert Einstein published his theory of general relativity, a new description of gravity built on the idea that mass bends space and time around it. Physicist John Wheeler later summed up the whole theory in one line: space tells matter how to move, and matter tells space how to curve. Barely a year after Einstein's papers came out, a German physicist named Karl Schwarzschild, working from the trenches during World War I, solved Einstein's equations for a single point of mass and found something strange hiding inside the math. His solution described a boundary in space where gravity became so strong that nothing, not even light, could ever cross back out again. Most physicists at the time treated this as a mathematical oddity, not a real object. Einstein himself doubted anything like it could actually exist in nature, and for decades the leading experts in general relativity were convinced such a thing could never truly form. Then in 1930, a young astrophysicist named Subrahmanyan Chandrasekhar calculated that stars heavier than a certain limit couldn't support themselves once they ran out of fuel. And in 1939, Robert Oppenheimer and Hartland Snyder worked out that a star roughly 3 times the mass of the Sun, or heavier, would keep collapsing forever, with nothing left to stop it. That math sat mostly ignored by the wider public for decades, filed away as a curiosity rather than a genuine feature of the universe. A new generation of scientists eventually picked the idea back up, gave it a name that finally stuck, and started looking for real proof it wasn't just theory. For most of the 20th century, scientists called these objects frozen stars, or gravitationally completely collapsed objects, clunky terms that never caught on with the public. In 1958, physicist David Finkelstein was among the first to describe the boundary around one clearly, as a one-way surface where nothing that crosses it can ever come back. In 1967, physicist John Archibald Wheeler used the phrase black hole during a lecture, and the simple, catchy name spread fast through both science and popular culture, replacing decades of awkward terminology almost overnight. A name wasn't proof, though. Proof needed a telescope pointed at the right patch of sky. In 1964, a short rocket flight above Earth's atmosphere picked up one of the brightest X-ray sources ever recorded, coming from the constellation Cygnus, and scientists named it Cygnus X-1. It took until the early 1970s for astronomers Charles Bolton, Louise Webster, and Paul Merton to work out what was actually happening there. A visible star was orbiting something unseen and incredibly massive, feeding it gas that heated up and blasted out X-rays as it fell in. The data matched what a black hole devouring matter should look like, and Cygnus X-1 became the first widely accepted real-world example, moving black holes out of pure theory for good. Decades later, scientists finally got something even Wheeler never had in his lifetime: an actual picture of one, built from a telescope the size of the entire planet. On April 10, 2019, a global team called the Event Horizon Telescope, made up of more than 200 researchers linking radio dishes across the planet, released the first image ever taken of a black hole's silhouette. Getting that image meant combining data from 8 observatories on 4 continents, all pointed at the same target during the same nights, with atomic clocks keeping every dish synced down to fractions of a second. The target was M87 Star, a supermassive black hole sitting about 55 million light-years away, weighing in at roughly 6.5 billion times the mass of the Sun. The image showed a bright ring of glowing gas wrapped around a dark center, exactly what Einstein's equations had predicted a century earlier. 3 years later, in May 2022, the same team released a second image, this time of Sagittarius A star, the much smaller black hole sitting at the center of our own Milky Way galaxy, weighing about 4.3 million solar masses. This one took even longer to produce than M87 star, since gas swirling around Sagittarius A star moves and changes shape within minutes, forcing the team to build entirely new tools just to average out the blur. Despite the huge size difference between the two black holes, both images looked remarkably alike, which told scientists that Einstein's gravity rules apply consistently no matter how big the black hole actually is. The Event Horizon Telescope team went on to win the Breakthrough Prize for Fundamental Physics in 2020, and researchers are already expanding the network to eventually capture actual video of a black hole's edge rather than a single still image. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. Both pictures showed the edge of these objects in stunning detail. What neither picture could show was what happens to anything that actually crosses that edge, and that is where the real violence begins. Any object falling toward a black hole gets pulled harder on the side closest to it than on the side farther away, since gravity weakens with distance the same way it does anywhere else in the universe. That difference in pull, called a tidal force, stretches the object lengthwise while squeezing it from the sides at the same time. Scientists gave this process a deliberately blunt name, spaghettification, because a falling body eventually gets stretched into a long, thin strand before it tears apart completely, exactly like a piece of dough pulled from both ends. How violent this process feels depends entirely on the size of the black hole doing the pulling. Smaller, stellar mass black holes pack their gravity into a tight space, so tidal forces spike hard and fast, tearing objects apart before they even reach the event horizon. Supermassive black holes, like M87 star or Sagittarius A star, spread their mass across a much wider area, so an object could theoretically cross the event horizon in one piece before the stretching becomes lethal, only getting shredded well after passing the point of no return. Researchers studying this math have calculated that tidal forces at the horizon of a small stellar black hole can be roughly 100 quintillion times stronger than the tidal forces at the horizon of a supermassive one. That size difference explains why astronomers actually get to watch this violence happen from a safe distance whenever a star wanders too close to the wrong kind of black hole. Tidal forces aren't just theory sitting in a textbook. When a star strays too near a supermassive black hole, the black hole's gravity can rip the star apart in an event astronomers call a tidal disruption event. Roughly half the star's material gets flung out into space while the rest spirals inward, heating up and glowing brightly enough for telescopes to spot from millions of light years away, sometimes even triggering a jet of particles blasted outward at close to the speed of light. NASA's X-ray telescopes, including Chandra and Swift, along with newer instruments like the Einstein probe, regularly catch the X-ray flashes these disruptions produce. Astrophysicists studying these events, including researcher Charlotte Mockler at UC Davis, describe the physics as the same tidal math behind ocean tides here on Earth caused by the sun and moon, just scaled up to a force strong enough to shred an entire star instead of moving a wave. Upcoming surveys from the Vera Rubin Observatory's Legacy Survey of Space and Time are expected to catch thousands more of these events in the years ahead, giving scientists a much bigger sample size to study. These flashes prove tidal forces are real and observable from Earth. No theory required. What they can't show is what happens after the wreckage disappears past the point of no return, because that's exactly where every known law of physics runs out of answers. At the very center of a black hole, according to general relativity, all of that crushed matter collapses down into a single point called a singularity, where density theoretically climbs toward infinity, and distances shrink toward zero. Einstein's equations simply stop producing sensible answers once you try to describe conditions at that exact point, which is why physicists often call it the edge of known science rather than an actual place. Physicists Stephen Hawking and Roger Penrose proved something important about this back in 1970. Singularities aren't just a strange side effect of overly simple math. They're an unavoidable outcome of general relativity under the right conditions, a result now known as the Hawking-Penrose singularity theorem. Some researchers now suspect real singularities may not even exist in the exact form the equations describe, and that a full theory blending gravity with quantum mechanics might reveal something else entirely once one gets discovered. Others have floated the idea that spinning black holes swap a single point for a thin ring instead, though that too remains unproven math rather than observed fact. Nobody has a combined theory of gravity and quantum mechanics yet, which means the singularity remains the sharpest edge of human ignorance in all of physics. Strangely enough, the next major discovery about black holes didn't come from what falls in, but from something almost nobody expected to come back out. For decades, black holes were assumed to be perfectly one-directional, swallowing everything and releasing nothing at all, matching the old idea that not even light could ever escape. In 1974, Stephen Hawking overturned that assumption using quantum mechanics. He showed that pairs of virtual particles constantly pop in and out of existence near the event horizon, and occasionally one particle from a pair falls into the black hole while its partner escapes outward as real radiation instead of vanishing back into nothing. This effect, now called Hawking radiation, means black holes technically lose a tiny amount of mass and energy over time, a slow process scientists call evaporation. For any black hole actually out there in space, this radiation is so faint it's effectively impossible to detect with current instruments, since the temperature it predicts is far colder than the background radiation left over from the Big Bang itself. Still, the theoretical discovery connected black holes to thermodynamics in a way nobody had managed before, giving mass a role similar to energy, surface gravity a role similar to temperature, and surface area a role similar to entropy. Hawking radiation solved one mystery while opening up an even bigger one, a puzzle that still doesn't have a clean answer even 50 years later. If a black hole slowly evaporates away completely through Hawking radiation, what happens to all the information about everything that ever fell into it? Quantum mechanics says information about a physical system can never be truly destroyed, but general relativity's version of a black hole seems to erase it completely, once matter crosses the event horizon and disappears from the observable universe. This contradiction is known as the black hole information paradox, and it has occupied some of the sharpest minds in physics for decades without a resolution everyone agrees on. Some researchers have proposed ways information might sneak back out through subtle patterns hidden in the escaping radiation itself, rather than being lost for good. In 2022, physicists Xavier Calmette and Steven Hsu published a series of papers arguing information could theoretically escape black holes through effects tied to quantum gravity, though the idea remains debated rather than settled fact among the wider physics community. The paradox shows just how incomplete our picture still is, and it gets even messier once you stop imagining a black hole that simply sits still and start looking at ones that spin. Schwarzschild's original solution described a black hole that doesn't rotate, which makes for a cleaner story, but doesn't match most real black holes in the universe, since almost everything that forms one starts out spinning already. In 1963, mathematician Roy Kerr solved Einstein's equations for a spinning black hole, and the results changed the picture significantly. Instead of a single point, a Kerr black hole's singularity theoretically takes the shape of a ring, a detail that has no equivalent in the simpler, non-spinning version. Spinning black holes also have a second inner horizon sitting inside the outer event horizon. Researchers studying this inner boundary, including physicist Tyler McMakin in a 2023 essay written for the Gravity Research Foundation, found that tidal forces near it can actually flip direction, first stretching a falling object like spaghetti and then flattening it like a pancake instead. Other studies on rotating black holes suggest an object might theoretically avoid the central ring singularity entirely by curving around it on the right path. Though this remains purely mathematical territory, nobody can ever test directly. None of this changes the basic outcome for anything real that falls in, but it shows how differently a black hole can behave depending on whether it spins. And that complexity is exactly why scientists keep hunting for new ways to study these objects up close. Every real black hole ever confirmed, from Cygnus X1 in 1971 to the image silhouettes of M87 star and Sagittarius A star, has been detected through indirect evidence, never a direct look inside. Gravitational waves picked up by LIGO in 2015, coming from two black holes colliding, added one more way to confirm these objects exist exactly as Einstein's math predicted a century earlier. What still hasn't happened, and likely never will, is a direct look past the event horizon. Tidal forces guarantee that anything crossing into a stellar mass black hole gets torn apart long before reaching the singularity, and no signal of any kind can ever travel back out to describe what's found beyond that edge. Everything past the horizon remains theory built on strong math, not proof, and that gap is exactly why physicists are still working on it. If you enjoyed this video, make sure to subscribe, and I'll see you in the next one.